Okay, today we're really going to lay some groundwork for, I guess, what's coming up second semester. So these are going to be some skills we need to really do the procedure we're going to learn second semester. Sample proportions. So today's lesson is all about proportions. These are the homework questions from last night, last lesson. So the sampling distribution of p hat. So p hat, we're talking about sample proportions here. Describes the distribution of values by the sample proportion p hat in all possible samples of the same population, same size from the population. So here's an exampling of the sampling distribution of, these are proportions, simulated proportion who support this particular proposal. Looks like around 50% of folks tend to support it. Oh, so, and this is the proposal they're supporting is that, do you think that the federal government should forgive all student loan debt? So about 50% think that we should. How to calculate that? Let p hat be the sample proportion. Okay, then the mean is just p. So the mean is nothing special. You don't have to calculate. Usually it's given to you. Standard deviation you will have to calculate for proportions. It's going to be p times the complement of p, or 1 minus p, all divided by n and all square rooted. And it also has to meet the 10%, less than 10% condition, right? So we've got to plug in numbers and prove that's true as well. Those are both included on the formula sheet. Super nice. In a large high school, 84% of students regularly use a backpack to carry their books. Imagine you take a simple random sample of 100 students, calculate the proportion of students in the sample who use a backpack. Calculate and interpret the mean of the sampling distribution of p hat. Well, the mean of p hat is p, is just 84%. So the mean, in this case, it's kind of weird to call it a mean because it's a proportion, the mean proportion, I guess you'd say. But the mean proportion is 84% or 0.84. Interpret that. So things you want to use here, if we took many samples, actually not even many samples, you really want to talk about, because of the sampling distribution, if you took all possible samples of the same size. So you want to start with, if you took all possible samples of the same size, approximately 84% of them would use a backpack. The sample proportions would have an average value of 84%. So if you averaged all those values, it would have a value of 84%. Verify that the less than 10% condition is met. Calculate and interpret the standard deviation of the sampling distribution. So before we can figure out standard deviation using that formula they just gave us, we've got to verify the less than 10% condition. So we took sample sizes of size 100. It's a large high school, think Collierville. There's 3,000 or 4,000 there, so it's definitely less than 10% of the entire student body at a large high school. So it does pass that condition, therefore we should be able to plug in the formula, p times the complement of p divided by n, all square rooted. So you would plug in the numbers for this one, and you get a standard deviation of 0.0367. It says interpret that value. Similar to the wording of this one, you start out the same. If you selected all possible samples of size 100 from the population, and calculated the standard deviation, it is 0.0367. The sample proportions would typically vary from the population proportion of 0.84 by about 0.0376. So that's a little different cadence than what we're used to. I think we're typically say standard deviations, typical deviation from the mean or different from the mean. But this is sample proportions would typically vary from the population proportion. We're not really going to the mean there. It's a population proportion of 0.84 by about 0.0376. So now we're talking about shape. And with proportions, we're hoping to prove that the data is approximate, that the sampling distribution is approximately normal. And so to do that, we've got to prove that NP has to be greater or equal to 10, and n times the complement of p, 1 minus p, is also greater or equal to 10. It's called the large count condition. Okay, so let's try this. So the 84%, let's just see if it fits the large count condition, right? So the formula was n times p is greater or equal to 10. So n is 100 here, right? And p is 0.84, so 100 times 0.84 is 84. Is that bigger than or equal to 10? Yes, it is. And then 100 times 0.16, is that bigger than or equal to 10? So if they are, so if you check both of them, and you'd have to check both of them, so you plug in the work, they like to see that work there. 100 times 0.84 equals 84. I like the way they put tacked on the end, greater or equal to 10. Just kind of a neat way of saying the whole thing in one sentence or math kind of equation there. Kind of a weird math equation, but you're trying to say that answer of 84 is greater or equal to 10. When you do it the other way, 16 is also greater or equal to 10. So that passes the large count conditions, which means we can say the data is approximately normal. The sampling distribution is approximately normal. So this is, again, the rule for proportions. Suppose that 35% of all first-year college students attend college within 50 miles of home. The polling organization takes a simple random sample of 1,500 first-year college students, how far their home is away from them. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the population percentage. Okay, so let's try to do this one. So I might think about doing the conditions first. So first, let's prove the less than 10% condition. So to prove that, you would say, let's see, less than 10%. So we have 1,500. So 1,500 is less than 10% of all first-year students. I guess in the United States, I mean first-year students. So that's the first condition, right? The next condition, that's the less than 10% condition, is the large counts. This will help us prove shape if we need it, which many times we will. So large counts is NP is greater than or equal to 10. So N is 1,500 times P is 0.35. That has to be greater than or equal to 10. I'm going to put it, that is going to be equal to something, which must be greater than or equal to 10. I like the way they wrote it the other time. Then 1,500 times the complement, or 1 minus 0.35, which is 0.65, should equal something that's also greater than or equal to 10. So if you get your calculator out, and you write 0.35 times 1,500. Oh man, way bigger, right? 525. And then 0.35, I'm sorry, 1,500 times 0.65, or 1 minus 0.35. Okay, so we've checked the conditions, which means we're ready to find the answers to the questions, right? So let's see how they did it. I think they did it in reverse order, maybe. Let's see. Defined p hat, that's a good thing to do. The notations for what we're finding here, so I think that's important here. Let me mention this. So the 0.35, that's going to be the mean of p hat, the mean proportion, so to speak, is 0.35. Standard deviation of p hat is going to be, I think it's square root of PQ, so 0.35 times Q, which is 0.35, times 0.65, all divided by N, which was 1500, I think. It should give you your answer for that one. So let's see what they did. They plugged in the numbers. They got the 0.0123 when they typed that in their calculator. They checked the large counts, the less than 10% condition. 15 is less than 10% of all first-year college students for sure. Because 15 times 0.35 is greater than or equal to 10, and so is 1500 times 0.65 greater than or equal to 10. The distribution is approximately normal. Okay, so I really like proving the conditions first. So there's two conditions. It's the less than 10% condition. So 1500 is less than 10% of, what are we going to put in there? First year students. I guess it's probably all first year students in the United States, and that's quite a few. So 1500 is definitely less than 10% of that. So that's the first condition that's been met. The second one, you have to do the large counts condition. But that one gives you, we can now do standard deviation. Large counts is NP, so 1500 times 0.35, which is equal to, I think 525, I believe. It's in my head, that could be wrong. Greater than or equal to 10. That seems to pass. Now we're not done. You got to do the other half of the large count conditions. 1500 times 0.65, which is 975, which is also greater than or equal to 10. So now it passes the large count condition. So now we can label stuff what it is, right? So the mean p hat is equal to, let's see, they gave it to us as 0.35. Standard deviation of p hat is equal to square root of 0.35 times 0.65 all over 1500. And you'll need to type that in your calculator to get that. 0.0123. And so because of that, we determined the distribution is, I would actually say approximately normal, not normal there. So approximately, because past the conditions, we know that it's approximately normal. Okay, so then we can sketch it out. And so it said within 2 percentage points of the population percentage. Well, 0.35 is the population percentage point, so it's got to be 2 percentage below, like 0.33, or 2 above, 0.37. And so if you do norm CDF with those lower bounds and upper bounds, and that mean and that standard deviation, you get the percentage, which is 89.61%. So that's the probability of having a random sample that's within 2 percentage points. This is just more practice, but you're done with the lesson portion of this. According to Pew Research Center, 32% of U.S. adults have a tattoo. Suppose this percentage is in fact correct. Imagine taking a simple random sample of 400 U.S. adults, calculate a p hat, the proportion of U.S. adults who have a tattoo. Calculate and interpret the mean of the sample sampling distribution of p hat. So the mean is 0.32, super easy. They give it to you. Interpreting is not so easy, so it's going to be if we took all possible samples, simple random samples of size 400 of the, what do we take the sample of the proportion of adults who have a tattoo, then the mean of those samples would be 0.32. They said it that way. You might want to look at their wording, but it's probably better. Verify the 10% condition is met. So 10% condition is, so 400 is less than 10% of all adults. Yeah, all adults. So I'm pretty sure that 400 is less than 10% of all U.S. adults. So that does pass the condition. calculate and interpret. So we got to plug into the formula there. So it's just the square root of 0.32 times 0.68 all over 400, all that square rooted. You get 0.0233. If you select all possible simple random samples of size 400 of people who have tattoos, the United States citizens who have tattoos, the sample proportion would typically vary from the, here's the kicker, it doesn't say vary from the mean, would typically vary from the population proportion of 0.32 by about 0.0233. You don't have to say what the population proportion is there, but you need to say typically vary from the population proportion by about 0.0233. Finally, the Pew Research Center says 32% of adults, we just read that, describe the shape of the sampling distribution. To do that, we first have to do the large counts condition. You would have to prove that so 20 times 0.32. Uh-oh, that doesn't work, right? So it doesn't pass the condition because 20 times 0.32 is 6.4. That's not bigger than 10, right? So we're not going to find the sampling, the shape here. We don't really know what the shape is. We don't think it's approximately normal, which is a problem here. I guess you would say it's skewed right. Let's see. Because P is less than 0.5, we think that it's skewed right. The big thing is it's not approximately normal. That's the big thing there. According to the current population survey, 14% of all U.S. adults, 25 and older, have completed an advanced degree. I've got a master's degree. Imagine taking a simple random sample of 1,000 U.S. adults, 25 and older, asking them if they have completed an advanced degree. Find the probability that the sample, 1,000 U.S. adults, age 25 or older, will get a result within 3 percentage points of the population percentage. So a very similar problem to what we've had before. I'm going to show you all the work for that. Again, you've got to check the conditions. The less than 10% condition, you've got to check the large counts condition. You've got to find the standard deviation. You've got to do, within 3 percentage points of the 0.14, so 0.11 to 0.17 there. Do your norm CDF once you've proved all that, and you get your answer. Great, that's your lesson for today.